Welcome back. We're gonna repeat the data structures and algorithms for more elaborate explanation. Why data structures matters. As software engineers gain more experience, though they begin to learn about additional layers and nuances regarding the quality of their code. They learned that there can be two snippets of code that both accomplish the same task, but that one snippet is better than the other. So as you progress through software engineering, you're gonna realize that there is two ways to accomplish the same task with the same code, and those could has different efficiencies in accomplishing that task. So there are numerous measures of code quality. One important measure is code maintainability. Maintainability of code involves aspects such as the readability, organization, and modularity of one's code. So the modularity or the flexibility of the code, the organization, how easy it is to learn for others, the readability, all of the design principles we've discussed are applicable here. However, there's another aspects of high quality code, and that is code efficiency. For example, you can have two code snippets that both achieve the same goal, but one runs faster than the other. So here, these are two codes that achieve the same task. Here is much faster than the first one. So we define a function, initiate the number 2, and we use a while loop. While here we use a nested if statement, which make it slower. Here we just use number plus equals to 2 instead, since we know how to that we want to accomplish that task early on. We were able to avoid this unnecessary action. This is also the reason why they are saying that the best code is no code, because as you can see, this has less code, but it's enormously faster than the first one. If you said version 2, you're right. This is because version 1 ends up looping 100 times, while version 2 only loops 50 times. So it's twice faster. The first version then takes twice as many steps as the second version. So it's the same with the previous video. We're still discussing time complexity as the number of steps to determine the efficiency of a code, because how can you improve the efficiency or the speed of a code if you don't know its current efficiency or speed or time complexity? The first step in writing fast code is to understand what data structures are and how different data structures can affect the speed of our code. So the first step in writing a fast code is to understand what is data structure. So a data structure is a way for us to organize data. So that is what data structure, and how those different data structure how does the measurement of those speed in different operations such as reading, inserting, deleting, and searching is applicable to a certain task that you want to improve. Data structures. So data is a broad term that refers to all types of information down to the most basic numbers and strings. In the simple but classic hello world program, the string hello world is a piece of data. It's a string. In fact, even the most complex pieces of data usually break down into a bunch of numbers and strings. Data structures refer to how data is organized. You're going to learn how the same data can be organized in a variety of ways. So a same data could actually be organized in a variety of ways with regards to code, or in computer it's memory, CPU, and your disk. So that's how you're gonna work on those limitations or on those technology to store this data. In design, however, we're working based on people's cognitive abilities. So this simple program deals with 3 pieces of data, outputting 3 strings to make one coherent message. If we were able to describe how the data is organized in this program, we'd say that we have 3 independent strings, each contained within a single variable. So if we were to describe this, we would say that we have 3 different strings of data that is stored in each in a single variable, such as hello are stored in a variable x, how are you string are stored in variable y, etc. However, this same data can also be stored in an array. So we stored that in 3 different variables. Now we're gonna store these 3 different variables in one array. So this is the difference between storing in variables and arrays. Also, remember in the previous video, we can actually store multiple variables in an array. So here, hello, how are you today? We just need to print the array 0, array 1, and array 3 instead of creating 3 different variables. So when you have a solid grasp on data structures, performance implications on the software you are creating, you will have the keys to write fast and elegant code, and your expertise as a software engineer will be greatly enhanced. The array, the foundational data structure, so this is not the only data structure that we have. We also have sets, we have heaps, we have queues, we have nodes. So these are just the foundational data structures. So most of data structures are actually stored in this way, or organized in this way, such as array. So an array is a list of data elements. The reason for that is for that simple variable that we've used in school, such as x, y, and z, we can actually store that in array. So those are one of the reasons, but this is actually how memory works, or how computers work. That's why it's so useful. It mimics a lot of how the computers store data. That's why it's the most foundational data structure. So an array is a list of data elements. If you're looking at the source code for an application that allow users to create and use shopping list for the grocery store, you might find code like this: array equal apples, bananas, cucumbers, dates, elderberries. These arrays happen to contain 5 strings, each representing something that I might buy at the supermarket. You've got to try elderberries. So this array or data structure are organized to represent something that you might buy in a supermarket. The size of an array is how many data elements the array holds. So the size of this is how many elements does the array holds. So these are actually data elements. So here 1, 2, 3, 4, 5. We have 5 data elements. And this array holds that 5 elements. And that is the size of the array. So that's actually what we see in codes like for loop. We usually use the something on the array that measures these data elements. We're gonna see that in the future videos. So our grocery list has a size of 5 since it contains 5 values. The index of an array is the number that identifies where a piece of data lives inside the array. So this list array, while having the 5 data elements, it also has a size of 5 since it has 5 values in each element. In most programming language, we begin counting the index at 0. So for our example array, apples is at index 0 and elderberries is at index 4. Data structures operation. So this is how most of the programming language starts with index 0. So aside from this, attributes that we use to describe this box inside this array, and then apples as the value of this index 0. So as you can see, we have two attributes of this basic data structure array. As we will later see in the future videos, these relationships and these boxes could get more sophisticated and nuanced depending on the task that we were trying to achieve with our code. Now, data structure operations. To understand the performance of any data structure such as the array, we need to analyze the common ways our code might interact with that data structure. So to analyze the performance, the speed, the efficiency, the time complexity of an array, we need to analyze the common operations which we've discussed in the previous video, namely reading, inserting, searching, and deleting. In this chapter, we'll analyze how fast each of these operations are when applied to an array. So these are the basic operations. We're gonna, for us to determine the speed of a data structure or the performance of that with regards to our code. Because again, remember, no code is the best code. But if we were to have this data structure for us to achieve our task, we need to determine how fast it is with regards to this basic operation. Or when applied to an array, many data structures are used in four basic ways, which we refer to as operations. These operations are read. Reading refers to looking something up at a particular spot within the data structure. With an array, this means looking up a value at a particular index. So a reading, meaning you're trying to find the value. So you already know this index. For example, looking up which grocery item is located at index 2 would be reading from the array. So if you looking and reading, kind of like the same, but as we will later see for searching, there's a nuance, because you could also use the word look for searching, right? Searching refers to looking for a particular value within a data structure. So let's say you don't know where the index, because the computer knows this index, that's why reading it is fast. As we will later see, it has like the fastest measurement for time complexity, because we divide the measurement for time complexity, I think, with five categories. So the first category is where reading at, because we already know the index, and as we will later see, computer are really good at remembering this index or the position of that value in the memory. Now searching, on the other hand, is like the opposite of reading, because you're trying to search the value without the actual index. So you need to look at each index on that array that you want to find. Of course, you will have to choose the array in the specific memory where those value might probably be located. Now searching refers to looking for a particular value within a data structure. It could be array, it could be set, it could be heap, it could be queue, it could be node. But the basic idea is you don't know the index yet, therefore you have to check each value. With an array, this means looking to see if a particular value exists within the array, and if so, at which index. For example, looking up the index of dates in our grocery list would be searching the array. Also, when we try to search a value, we'll eventually get the attribute index as well. For example, looking up the index of dates in our grocery list would be searching the entire array. Insertion refers to adding new value to our data structure. So we're gonna add value, not index, because index will automatically be added because it's just a position in memory to that along with that value. And also one of the characteristics of this array is actually the insertion at the end is the fastest. So that's the best case scenario. While inserting at the beginning is the worst case scenario, because of the characteristics of computers or memory that or array rather, that you can only insert at the end for the best case scenario. So here, insertion refers to adding a new value to our data structure with an array. This means adding a new value to an additional slot within the array. If we were also, another thing is that the array is not efficient if, let's say, you insert at the middle and then you ship it to the right and then there's like empty array, it will not be efficient when it comes to its operations, these basic operations, and when it comes to interacting with that data. Of course, interface, you're trying to insert data and then there's a function. So as data grows, as your user interact with that functions or algorithm, you can't have those empty space. So insertion refers to adding a new value to our data structure with an array. This means adding a new value to an additional slot within the array. If we were to add fixed to our shopping list, we'd be inserting a new value into the array. Deletion refers to removing a value from our data structure. So again, it's the same. We're removing a value, not the index. With an array, this means removing one of the values from the array. For example, if we remove bananas from our grocery list, this value would be deleted from the array. Measuring speed. We've actually seen this in the context of printing the even numbers from 2 to 100 before. The first example. The second version of that function was faster because it took half as many steps as the first version did. However, we can measure the speed of an operation in terms of how many computational steps it takes. So the reason why we mention it time complexity even though we're measuring steps is because we cannot really determine the time that the code accomplish the task, because there is a lot of factors such as the hardware where the computer runs the task, the actual task, the environment, the hardware, the network, how fast the internet, the user, of course. But here we're just trying to determine the efficiency of the code. So the code, to determine the efficiency, the key concept is to determine the steps, like what I've mentioned in the previous chapter. So however, we can measure the speed of an operation in terms of how many computational steps it takes. If operation A takes 5 steps and operation B takes 500 steps, we can assume that operation A will always be faster than operation B on all pieces of hardware. Throughout these videos, I'll use the terms speed, time complexity, efficiency, performance, and runtime interchangeably. So this time complexity, the efficiency, the steps, runtime are all actually the same in this throughout this video, and really the same in the real world as well. If you're just looking at it at a speed point of view or of the code alone without the hardware, the user ability to learn, and the network. So they all refer to number of steps a given operation takes. The first operation will look at is reading, which look at what value is contained at a particular index inside the array. So like what I've said, we already have an index, so we are trying to find a value. A computer's memory can be viewed as a giant collection of cells like this. In the following diagram, you can see a grid of cells in which some are empty and some contain bits of data. So later we will discuss how this is kind of similar to the node data structure, which could have this discontinuous data at a different cells of the memory. So it's not like an array where this an array could not have that empty space. So when a program declares an array, it actually, so when we write those code in the first chapter here, it especially for an array like this, it allocates a contiguous set of empty cells for use in the program. So contiguous, it's not discontinuous like a different data structure like node. So if you were creating an array meant to hold 5 elements, your computer would find a group of 5 empty cells in a row and designate it to serve as your array. Now this is where the data that will come, such as the apples, bananas, cucumbers, dates, elderberries. As this is the part of the memory where you will add the the value. So as you can see, there's already an index, but there's no value yet. But different operations in this subset of cells in the array has different speed or different steps to accomplish depending on the operations, of course, and depending on the data structure. But in this case, we're just representing an array. So now every cell in a computer's memory has a specific address. It's sort of like a street address, for example 123 Main Street, except that it's represented with a number. So it's like a street address, except like it's represented by a number. So the computer already knows this at hand, and it keeps that memory while the computer is turned on, or it keeps these attributes or index number while the computer is turned on. Each cell's memory address is one number greater than the previous cell's address. So these are the characteristics that I'm talking about earlier, is that each cell's memory is addition of the previous one, such as 1000, 1001. Here's a visual that show each cell's memory address. Now in the next diagram, you can see our shopping list array with its index and memory address. For apples, it's 1010, which is index 0. As you can see, we really have three attributes. But for most programming language, they just add this third attributes, that for an specific allocated contiguous array, you start with 0. So let's say in this contiguous memory, this is where it is located. This subset of cells starts at 1010. Therefore, you got this look. So memory address, index, and the value. Now when the computer reads a value at a particular index of an array, it can jump straight to that index because of the combination of the following facts about computers. So this is the details why the reading or operation takes the fastest. So a computer can jump to any memory address in one step. For example, if you have a computer to inspect whatever's at memory address 1063, it can access that without having to perform any search process. So it doesn't need to search process. So the reason why it is called search operation, and it's not reading, where you're trying to search for along the index a subset of contiguous array here, and then searching for value and then comparing it with the one you're searching, is that you're actually searching it. So here, as you can see, a computer can jump to any address in one step. For example, if you ask a computer to inspect whatever's at memory address 1063, since the computer have that at the same time, due to the nature of memory or the technology, when it is turned on, it actually have that capability to remember this many numbers. Now it can access that without having to perform any search process. As an analogy, if I ask you to raise your right pinky finger, you wouldn't have to search all your fingers to find one which is your right pinky. You'd be able to identify it immediately. So it's kind of like, yes, what I've discussed in the previous video is that your memory, kind of like what you've studied in college after. So if you grow older, the one you studied in college or the one you've worked um, before you're 25 years old will become your memory, because you'll be able to get that those information will be stored in your long-term memory, kind of like become your intuition or second memory. So you'll be able to raise your right pinky finger, it become part of your body. Now, with another fact is that whenever a computer allocates an array, it also makes a note at which memory address the array begins. So another key is that the computer does not randomly allocates this subset. It also takes note where this array start, so that it can keep adding it. Kind of like in the memory and the CPU handles this itself, without you having to interact with this. So if we ask the computer to find the first element of the array, it would be able to instantly jump to the appropriate memory address to find it. So if we ask the first element, such as this index 0, the computer will be able to jump into it, because it is the one that allocate that array or contiguous subset of cells to the data to begin with. So as we will later see in the future videos, we allocate, since we know this, we actually use that in our programming language to be able to access that data in the memory. So we're actually this is the the syntax we'll be using to define the for loop, like the loop, since we discussed in the previous video that we're actually using for loop, while loop, if else statement, those things to actually make a program or an algorithm to accomplish a certain task. Now those certain tasks actually are just transported to this GUI, graphical user interface, through controls and idioms, right? So that's how computer works. So most of the time, these algorithms and data structures, or the code, the one we're using in code, is actually already created for ourselves. We don't need, so we can focus on solving new problems. But for us to understand how that has been created in the first place, we need to create that code. So that's actually where the code, the knowledge of algorithm, is valuable, because on that level of detail, this is actually how we make it efficient, by understanding how this operation works at a deep level. So if we ask the computer to find the first element of the array, it will be able to instantly jump to the appropriate memory address to find it, because again, that's the one that allocated it in the first place. Let's apply this to our grocery list array. Our example array begins at memory address 1010. So if we told the computer to read the value at index 3, the computer would go through the following thought process. The array begins with index 0, which is at memory address 1010. Index 3 will be exactly 3 slots past index 0. By logical extension, index 3 would be located at memory address 1013, since 1010 plus 3 is 1013. Once the computer knows that index 3 at memory address 1013, it can jump right there and see that it contains the value dates. So that's actually the thought process of computers. You can see it's logical. It knows addition, of course, because it's using XOR, and then the logic gates at the CPU, which are kind of amazing in the uh, lower level details of the things such as the assembly language, but this is actually how it thinks. So it just convert that programming language into this lower level details. So besides being a foundational data structure, R is also a very powerful data structures because we can read from them with such speed. So again, we're just talking about RE for us to understand how the efficiency of data, of how we organize the data in our memory, will affect how fast we accomplish the task and how we will be more effective as a developer. So again, the data structure, we discussed this, the reading. So these are the reading operation speed for the array, but does not mean that it will be the data structure for all the subsequent data structure. Sorry, I got confused. So, but that doesn't mean that this is the operation that will be. This is the speed of the reading operation that will be applicable for all the subsequent data structure. We're just using this because it's such a foundational data structure in computer science. Searching, on the other hand, means providing the computer a value and asking it to return the index of that value's location. Now you're trying to ask the index, so you're kind of trying to ask here these two attributes 1010 and 1, or 1010 and 0, and you have this value, so you have to look at it because here's what it looks like. It has question mark. So reading from an index is fast since a computer can jump immediately to any index and discover the value contained there. Searching, though, is tedious since the computer has no way to jump to a particular value. To the computer, the array looks something like this. To search for a fruit within the array, the computer has no choice but to inspect each cell one at a time. So the computer has to work hard on it. So again, we're trying to work on the technological constraints of the memory of the computer. That is why we're trying to improve the data structures and the type of operations we do on our data structures and the type of algorithm we're trying to create. So that's actually the reason why we're doing this data structures and algorithm. Now, to search for a fruit within the array, the computer has no choice but to inspect each cell one at a time. The following diagrams demonstrate the process the computer would use to search for data within an array. So here we start with the apple, it's not the dates. Then banana, it's not the dates. Cucumber, it's not the dates. Then we find the dates. So as you can see, at this point, the computer does not need to move on to the next cell of the array since it already found what we're looking for. So since we're searching for that data structure, for searching, of course, there's an algorithm for us that we're gonna use that are designed to stop at that certain point. But we will later discuss that in the future videos. But for now, let's just be concerned on the search operation in we're trying to analyze the search operation in array. Now in this example, because the computer had to check for different cells until if it found the value we're searching for, we'd say that this particular operation took a total of 4 steps. So yeah, it took us 4 steps because, first apple, etc. Now, in why algorithms matter, you'll learn about another way to search an array. But this basic search algorithm, in which the computer checks each one cell one at a time, is known as linear search. So there's a code for that, which designed to start at the first index until it reach or find the value on that specific subset of array. But later, there's another way to search for that, in which you divide this, you start with the middle, as long as this is an ordered array. But an ordered array is a different kind of array. It's different from the classic array in which these are ordered in terms of, its numerical value, such as 1, 2, to up, right? So you start with 1, that's why it's ordered. Now, another way of saying this is that for n cells in an array, linear search would take a maximum of n steps. So another way to analyze that time, which is the actual second part of time complexity, or how we measure the speed. So remember, measurement is a key for us to improve the efficiency. So these n steps, as we will later see, is kind of it's kind of slower than first steps reading. So searching has this, is slower than reading basically. We will discuss this further in the later chapters. Another way of saying this is that for n cells in an array, linear search would take a maximum of n steps. So for n cells, or for n data elements, a linear search, so whether it's running in this computer, whether it's working from this type of people that is slow and that is fast learner, or whether it has fast or slow network connectivity, for that type of searching, for that data, for an array data structure, we would say that it will take n steps for us, or the number of data elements for us to search for that. Therefore, in this context, n is just a variable that can be replaced by any number depending on the number of elements. So that's the time complexity, or the number of steps would take for searching for this type of data structure. Now for insertion, the efficiency of inserting a new piece of data into an array depends on where within an array you're inserting it. Another fact about computers is that when allocating an array, the computer always keeps track of the array size. So this array size will come up again and again, especially in our code, because this array size, we're gonna use this to look into this data. For example, this, we know that this for 1, 2, 3, 4, 5, 6, we know this has a 6 data element, so that's its size. Now, we're gonna actually use that for insertion operations as well. But we don't just know the size, the computer don't just know the size, it also knows the corresponding memory address. And therefore, we can use our code, since it starts with index 0, to iterate this. So that's actually how we're using the code, which we'll gonna later dig dive for the actual code creation of this. Now, when we couple this with the fact that the computer also knows at which memory address the array begins, computing the memory address of the last item of the array is a cinch. So computing the memory address for that array, since we already know the size, so and we know where that index started, so because that's the fact about a computer. If the array begins at memory address 1010 and its size is of size 5, that means its final memory address is 1014. So it knows that the last data. So to insert an item beyond that would mean adding it to the next memory address, which is 1015. So, but there's one hitch, because the computer initially allocated only 5 cells in memory. So since it allocated initially 5, and then you're gonna add for the array, and now we're adding a 6th element, the computer may have to allocate additional cells toward this array. In many programming language, this is done under the hood automatically, but each language handles this differently. So I won't go into the details of it. So for many programming language, those are handled automatically. It allocates memory. But in some cases, you will have to write code for it yourself. Now we've dealt with insertion at the end of an array. But inserting a new piece of data at the beginning or in the middle of an array is a different story. So that's where the different best case, worst case, and the average case scenario will come. Because most of the time, it's the same with the design videos. It's the average that happen. But in this determining the efficiency of a data structure, we're trying to usually measure the worst case scenario, because if we measure the worst case scenario, therefore we are confident that that is the most likely speeds even in the worst case scenario. That's how it measures in terms of its steps. Now, we've dealt with insertions at the end of an array, but inserting a new piece of data at the beginning or in the middle of an array, at the beginning, which is the worst case, inserting at the end is actually the best case of an array data structure, or in the middle of an array is a different story. In these cases, we need to ship pieces of data to make room for what we're inserting, leading to additional steps. So that's less efficient, because aside from inserting, which is has itself a step, moving or shifting it, which is another step, which gonna dig dive in the future videos, is another type of step. So to do this, we need to move the cucumbers, dates, and elderberries to the right to make room for figs. So let's say we want figs on index 2. So we need to move this to the right, index 0, 1, 2. So after bananas. So this takes multiple steps, since we need to first move elderberries one cell to the right. So the computer will allocate this automatically. You need to move that to the right first to move dates. So here we move the elderberries to the right first, and then we move dates to the right, and then we move cucumber to the right, and then we insert the figs. Now we can say that insertion in a worst case scenario can take n plus 1 steps for an array containing n elements. So kind of like the searching. For searching, you're always gonna search depending on the number of elements. But of course, it has a best case, worst case, and average case scenario. If it's at the beginning, so you're starting the search at the beginning of the index usually, if you're using linear search. Therefore, the speed of that would be O1. But we're not trying to measure that. Again, we're trying to measure the worst case for us to be sure that this is actually the efficiency of these operations for this typical type of data structure. We can say that insertion in a worst case scenario can take n plus 1, because the number we need to ship in n steps, and then 1 for inserting for an array containing n elements. This is because we need to shift all n elements over and finally execute the actual insertion step. Now that we've covered insertion, we're up to the array finals operation, deletion. Deletion from an array is the process of eliminating the value at a particular index. Let's return to our original example array and delete the value at index 2. In our example, this value is cucumbers. Step 1, we delete the cucumbers from the array. An array is not effective when there are gaps in the middle of it. So to resolve this issue, we need to ship dates and elderberries to the left. Again, an array, so it is just a specific to array data structure, is not effective when there is an empty value in the middle. This means our deletion process requires additional steps. So we shift the dates to the left here, and then ship elderberries. Now you have those additional at the end. Those for array could be deleted, just like inserting at the end, right? Takes the best case scenario. So we can delete that, or the computer can delete that easily, that empty allocation. Now we shift elderberries to the left. It turns out that for this deletion, the entire operation took 3 steps. So the first step involved the actual deletion, and the other steps involve data shift to close the gap. So as you can see, the deletion and the insertion has a shift step, which actually not in the four basic operation, but it's kind of involved in the not kind of, it's involved in insertion and deletion operation. So for insertion and deletion, you're actually doing two steps, namely insertion and shifting, and deletion and shifting. Now, the first step involved the actual deletion, and the other two steps involved data shift to close the gap. Like insertion, the worst case scenario of deleting an element is deleting the very first element of the array. So if you're gonna delete this is the worst case, just like insertion, because you need to shift all that the n elements on the array to the first allocation. For an array of 5 elements, we'd spend one step deleting the first element, just like insertion, and 4 step shifting the 4 remaining elements. For an array of 500 elements, we'd spend one step deleting the first element and 499 steps shifting the remaining data. So it's kind of like n speed, so which is another category of time complexity. We can say that then that for an array containing n elements, the maximum number of steps that the deletion would take is n steps. Kind of like the same with insertion. Now, sets, how a single rule can affect efficiency. There are different, so sets is still an array, it's just that it doesn't allow duplicate values. So there are different types of set, but for this discussion, there's different data structure inside this set. A set is kind of like an abstract data type that just don't allow duplicate value. Now in this section, we're gonna discuss an array-based set. So the data structure is an array, but at the same time, the overall concept is it doesn't allow duplicate values. This set is just like an array. It's a simple list of values. The only difference between this set and classic array is that the set never allows duplicate values to be inserted to it. For example, if you had the set ABC and tried to add another B, the computer just wouldn't allow it since B already exists within the set. Now, while not allowing duplicates is a useful feature, this simple constraints also causes the set to have a different efficiency for one of the 4 operations. Though that duplicate feature is certainly useful for certain use cases, it affects the operations, the reading, deletion, insertion, and searching time enormously, as we will later see. So let's analyze the reading, searching, insertion, and deletion operation in the context of an array-based set. Reading from a set is exactly the same as reading from an array. It takes just one step for the computer to look up what's contained within a particular index. So for this type of array, the reading is also one step, which is fast. Searching a set also turns out to be no different than searching an array. It takes up to n steps to search for a value within a set, and deletion is also identical. Between set and array, it takes up to n steps to delete a value and move data to the left to close the gaps. Insertion, however, is where arrays and sets diverge. Let's first explore inserting a value at the end of a set, which was a best case scenario for an array. So insertion operation where has insert and shift is where it differs from duplicate to a regular array. Now let's first explore inserting a value at the end of a set, which was the best case scenario for an array. We saw that with an array, the computer can insert a value at its end in a single step. So for array, the computer can easily insert it at its end. Now with the set, however, the computer first need to determine that this value doesn't already exist in this set, because that's what sets do. They prevent duplicate data from being inserted to them. Because of this, the computer will first need to search the set to see whether the value we want to insert is already there. So instead of just inserting at the end without worrying about the duplicate, you have this additional operation which is search. So for inserting, the operation kinda have to be included. The search operation needs to be included in inserting operation of an array set. So I don't know if you get that. Again, I'm gonna repeat. For insertion operation, a searching operation needs to be included. So there's two operations. Before you insert it, you need to search. You do the search operation to make sure that that is not already in that array. So with the set, however, the computer first need to determine that this value doesn't already exist in this set, because that's what set do. Because of this, the computer will first need to search the set to see whether the value we want to insert is already there. Only if the set does not yet contain our new value will computer allow the insertion to take place. So every insertion into a set requires a search. So here you search index 0 for fix. It's not there, but it might be somewhere else in the set. We need to make sure fix does not exist anywhere before we can insert it. Search index 1, search index 2, search index 3, search index 4. Now we have first four search steps. Now that we've searched the entire set, we know that with certainty that it doesn't already contain figs. At this point, it's safe to complete the insertion. And that brings us to our final step, step 6. Insert figs at the end of the set. So for 5 elements, for inserting, usually you need to add 1 because of the insertion step. So for insertion, for a regular array, it just take n step. While here, you did additional 1 because for searching an array, it takes an n steps and then additional 1 for the actual insertion. Said another way, insertion into the end of a set will take up to n plus 1 steps for n elements. This is because there are n steps of search to ensure that the value doesn't already exist within the set, and then 1 step for the actual insertion. Contrast this with a regular array in which such insertion takes a grand total of 1 step. In the worst case scenario, where we're inserting a value at the beginning of a set, which we need to shift this away, the computer needs to search n cells to ensure that the set doesn't already contain the value, another n steps to shift all the value, so that's 2n, and another final step to insert a new value. So that's a total of 2n plus 1 steps. As in the future video, this 2n plus 1 steps is just one category of n steps. This constant doesn't really matter for measuring this speed. Contrast this to insertion into the beginning of a regular array, which only takes n plus 1 steps. So for regular array, it's only n plus 1 steps. But we're just trying to find the new ones here. For insertion, the insertion operation, so if you're expecting your application to insert something more often, then this duplicate array is not the right array or data structure for you to improve the speed of your code. Now, does this mean you should avoid set just because insertion is lower for sets than regular arrays? Absolutely not. Sets are important when you need to ensure that there is no duplicate data. So it's still important if you want to ensure that there's no duplicate data, such as like same name in your contact numbers, etc. It's immensely important. But when you don't have such a need, an array may be preferable since insertion for an array are more efficient than insertion for sets. So if you don't need or you don't worry about that duplicate data, then a regular array will suffice. You must analyze the need of your own application and decide which data structure is a better fit. Why algorithms matter? In the previous section, we've learned that even two data structures that seem so similar, such as the array and the set, can have a different levels of efficiency. In this chapter, we're going to discover that even if we decide on a particular data structure, another major factor can affect the efficiency of our code, the proper selection of which algorithm to use. So the search operation, which we use to determine and to analyze the efficiency and the speed of steps in an array, such as the linear search for our searching, is actually an algorithm. So as you can see, it's interconnected. But now we're trying to discuss those specific algorithm itself, which is the linear search. When applied to computing, an algorithm refers to the set of instructions given to a computer to achieve a particular task. When we write any code that set to accomplish any goal that does not have any error, so remember, the writing or the goal of the usual software engineer is not to make the code work so that they don't have error. They want to focus on debugging and to make it work. But to actually make your code efficient, you need to understand the data structure underlying that code and the algorithm it does, such as that linear search operation. So any code really that we use to achieve a certain task, even though a simple storing of variable value is actually an algorithm, and then printing it is an algorithm already. Now, when we write any code, then we're creating algorithm for the computer to follow and execute. So the allocation, though it's a data structure itself, it's a good example of how we can measure the speed of different data structures, such as the most fundamental, which is array. An algorithm that used to that is actually the one that allocates that memory to the computer. Now, when we write any code, then we're creating algorithms for the computer to follow and execute. So that's what the computer are gonna execute. So that is the top level, kind of like when the computer converting that to assembly language, then to lower detailed instructions such as SOR, SOR, NOR, different electronic steps. But those have been abstracted to us for us to create this programming language. Now, actually, we can use AI to command computer what we want to do using our learn agents on the GUI. So we don't even need to know the details. We just need to know the specific high level on what we need our computer to do. Of course, we need to understand the intricacies, the speed, the UI, the memory, how it stores data. But on a high level, we don't need to worry about debugging. That used to be the goal of developers before, which is to make it work, right? And then the efficiency, they try to look the efficiency when they try to learn data structures and algorithms. Now, sometimes it's possible to have two different algorithms that accomplish the same task, but different efficiency or different speed, kind of like the way we measure the data structures, such as O1 and N step. Later, we will gonna see a different speed, such as exponential logarithms, etc. So here, we will discuss ordered arrays. So the ordered arrays, it's not really the way computers or programming language sort the to ascending or to date the app that you're using, such as Shopee or Amazon. It's not the way it used that, but it's kind of like the same concept. It orders the data inside the array. So the ordered array is almost identical to the classic array we saw in the previous chapter. The only difference is that ordered arrays requires that the values are always kept, you guessed it, in order. That is, every time a value is added, it gets placed in the proper cell so that the values in the array remain sorted. So every time you insert a value, so if you want to insert like that insert operation, you're gonna use that as an algorithm. Of course, there's a search, right, for insertion. for duplicate. But for ordered array, there's a search as well, because there's kind of like a search, because you need to determine where in that cell or in that position in the memory you would add that data. So for example, let's take the array 317 18 202. Assume we want to insert the value 75 into the array. If this array were a classic array, we would insert the 75 at the end as follows. But it's not a classic array, it's an ordered array. As we saw in the previous chapter, the computer can accomplish this in a single step. So the computer can, since it's still an array, it has the same properties in that you can insert it at the end of the index in one step, or the speed is nice, right? On the other hand, if this were an ordered array, we'd have no choice but to insert the 75 in the spot so that the values remain in ascending order. But this requires that the computer knows the values in each, right? So as you can as we've discovered earlier, the computer not necessarily know each value on this array. Now, this is easier said than done. The computer cannot simply drop the 75 into the right slot in a single step, because it first has to find the right place to insert the 75 and then shift the other values to make room for it. Let's break down this process step by step. So we need to search, a search operation, and then of course we need a shift step. So kind of like in insertion and deletion, you have a shift, right? So in search, here a different type of array requires us to search, at the same time shift first before we can insert. So based on that alone, we can determine that the time complexity or the speed of the steps needed to accomplish that task is different. So now this is easier said than done. So here, let's start again with the original ordered array. Step 1, we check the value at index 0 to determine whether the value we want to insert, the 75, should go to its left or its right. Because 75 is greater than 3, we know that the 75 will be inserted somewhere to its right. So in here, inside the code, we're actually using a comparison, whether it's less than or greater than. However, we don't know yet exactly which cell it should be inserted into, so we need to check the next cell. We'll call this type of step a comparison. So here we introduce a new step. In our searching, we're just not searching for the value or checking the value of each index. We're introducing a new step, which is a comparison. We're checking if it's less than or equal to the value we want to insert, where we compare the value. We're inserting a number already present in the ordered array. Now step 2, we inspect the value at the next cell. 75 is greater than 17, so we need to move on. Step 3, we check the value of the next cell. We've encountered the value 80. So this is the only time this number shown on the computer. So you can imagine this as a question mark, because the computer doesn't know the value yet. It needs to search for that. But since it's found the 80 is greater than, we know where to put the 75, right? But the code needs to work, or the array are designed to work, to be inserted into that position. So as we will later see in the codes, we've encountered the value 80, which is greater than the 75 we wish to insert. Since we've reached the first value that is greater than 75, we can conclude that 75 must be placed immediately to the left of this 80 to maintain the order of this ordered array. To do this, we need to shift date to make room for the 75. So this is where the shifting. As you can see, we first do the comparison and then shift. Move the final value to the right. Move the next to last to the right, 80. So since we've tracked that where the index, or where the less, or the previous node, or sorry, the previous index where we should put that 75, therefore we were able to can finally insert the 75 into the correct spot. Now it emerges that when inserting into an ordered array, we need to always conduct a search, or comparison before the actual insertion to determine the correct spot for insertion. We can see in this example that we were initially 4 elements, and that insertion took 6 steps. In terms of n, we'd say that for n elements in an ordered array, the insertion took n plus 2 steps in total. Since we have 4, as you can see, we have 6 steps. We have how many? So for these 4 elements, we actually have n plus 2 steps, but that is not the same for all arrays. What if it's, at the end, right? So that's the worst case scenario. Interestingly, the number of steps for insertion remains similar no matter where in the ordered array our new value ends up. Sorry, let me rephrase. So no matter where we need to put this new inserted value, the number of steps for insertion operation is n plus 2, namely comparison and shifting. If our value ends up toward the beginning of the ordered array, we have fewer comparisons and more shifts. So that's the difference. Though we do have fewer comparisons, if it's in the beginning, we have more shifts. If our value ends up toward the end, which is here, which we thought would be the worst case, we get more comparison but fewer shifts. While insertion is less efficient for an ordered array than for a classic array, the ordered array has a secret superpower when it comes to searching, which we will discuss in the future videos, which is the binary search. So instead of searching it linearly, each one, since it's ordered, though the insertion operation that could be applied to that is lower than a classic array, the searching operation could be faster if you use a different algorithm, namely binary search. The fewest steps occur when the new value winds up at the very end, since no shifts are necessary. In this case, we take n steps to compare the new value with all n existing values plus 1 step for insertion step, yielding a total of n plus 1 step. So overall, it's kind of like the same in any part of the array. But this ordered array, as we will later see, are mainly used for a different type, of optimization, which is searching. Because if it's ordered or if it's ascending, it's easier to search. Kind of like in your favorite e-commerce applications such as Amazon or Shopee.